Hi, I'm Mike Neal, LabVIEW Product Manager here at National Instruments. Over the next few minutes, we'll examine how you can use LabVIEW to create your own test, control, and embedded applications. In our demonstration, we'll acquire live data and display that data on a custom user interface. LabVIEW applications are found in many different industries. A LabVIEW program might test consumer electronics, control a machine autonomously, monitor conditions in an industrial environment, or prototype the embedded logic in a biomedical device. Kids even use LabVIEW programming to control the Lego Mindstorm robot. All of these applications have a few things in common. They each require physical measurements and I/O, analysis and signal processing, complex decision making, data logging, and report generation and communication. You may even want to run your LabVIEW program on Mac OS X, Linux, or a real-time or embedded system. We'll now introduce you to the LabVIEW environment and develop a custom application from scratch. We'll start by launching LabVIEW, which brings up the Getting Started window. From here you can access fundamental information like getting started with LabVIEW, the LabVIEW help, information on new features, as well as web resources like the discussion forums and LabVIEW Zone. I'll begin by creating a new LabVIEW program, which is known in LabVIEW as a VI. A LabVIEW VI consists of two major components: a block diagram where you develop the code, and a user interface where you can customize objects like graphs, knobs, and buttons. For now, let's focus on the block diagram. In LabVIEW, you wire together graphical blocks on the diagram to create your program. Each block has inputs and outputs, just like a function in a text-based language. When a block executes, it produces data, which passes down the wire to the next block. The movement of data determines the order of execution of the program. Now that you understand this concept, we're ready to begin programming. We'll create a temperature monitoring application with alarming and file I/O. In order to acquire our data, we'll use this National Instruments USB-based data acquisition system known as Compact DAC. In this chassis, I have several modules, including a thermocouple module with a thermocouple already attached. I've already connected my Compact DAC chassis to my laptop, so I'll begin my acquisition by dropping down a block for acquiring data from my thermocouple module. I'll do this by right-clicking and bringing up what is known as a palette. A palette in LabVIEW is where you get the functions that you use to create your block diagram code as well as your user interface. I'll navigate to my Express palette, go to the Input subpalette, and grab something called the DAC Assistant. I'll place this on the block diagram and then interact with it through a configuration dialog. In this dialog, I can tell it that I want to acquire an analog signal. I know this measurement is for temperature, and I know that I have a thermocouple. I'm using a 9211 module, and that thermocouple is connected to channel 0. When I press Finish, it brings up a second dialog where I can configure additional settings such as triggering, advanced timing, or even simple things like min and max temperature. I'll use 80 degrees and 30 degrees as my min and max for degrees Fahrenheit. And then I'll press OK. Behind the scenes, LabVIEW will configure the DAC Assistant VI so that it talks directly to my hardware and acquires my data for me. Next, let's perform some analysis on the data. To ensure that my temperature reading is accurate, I'll take several values and average them to produce a mean. To do this, I'll access my palettes and access the Signal Analysis palette where I can find my Statistics VI. When I drag this to the block diagram and drop it, I'll see another configuration dialog where I can select Arithmetic Mean and press OK. Now, as I mentioned earlier, order of execution is determined in LabVIEW through data flow. Therefore, to perform the mean calculation on the acquired data, I must wire the output of the data acquisition block to the input of the statistics block. To prove that our program is working, let's view the mean value on the user interface. One of the most common ways to view your data on the user interface is with a chart. I can right-click on my user interface and bring up the Controls palette. When I go into the Graph subpalette and grab the waveform chart, I can place this on my user interface and resize it to fit my needs. I can even go in and customize the color of the line that I'll see once I have my live data, as well as the line width. Lastly, in order to see the data on the user interface, I need to wire the output of the statistics VI to the input of the waveform chart. While getting a single value may be useful, it's more common to run an application continuously until a stop condition occurs. Like text-based languages such as C, LabVIEW contains programming concepts such as for loops and while loops. We'll add a while loop to this program around our code so that it runs continuously until we press the stop button. We'll start by right-clicking on our block diagram and grabbing a while loop from our structures palette, and then taking this while loop and placing it around all of our code. Now you'll notice, if you look at the upper left-hand corner of the menu, that the run arrow is now broken. This occurs because LabVIEW is continuously evaluating the correctness of your code, and if it finds a problem, displaying that through the broken run arrow. Once you click on the broken run arrow, it'll give you feedback on errors and warnings. In this case, the terminal condition that tells the loop when to stop has not been wired. This must be done before the program can be run. So I'll press OK here. Right-click on the terminal condition and say Create Control. And you'll notice that I now have a stop button on my user interface that I can resize. As you can see, the run arrow is no longer broken, and we're now ready to run our program and see what happens. I'll do this by clicking on the run arrow in the upper left-hand corner. And you'll notice that immediately I start sending live data trending across the screen. The temperature in the room is approximately 72 degrees. But what I can do is press on the thermocouple, and that temperature will rise dramatically. Once I let go, the temperature reverses its trend and goes down. We can also add more sophisticated functionality to our program, such as alarming. To get started, I'll place a slider control and a Boolean control on the user interface. To do this, once again, I'll right-click and go to my controls palette. I can access Booleans under the Boolean subpalette, so I'll drop this round Boolean. And as I mentioned earlier, you can completely customize whatever you put on the user interface, so I'll resize that control. I'll also go into the controls palette and grab a numeric slider. Once I place this on the user interface, I can also resize it. On the block diagram, I'll alter my program so that the Boolean blinks when the temperature reading is above the limit we set on the slider. In order to do this, I'll begin by going into my functions palette and going into the comparison subpalette and grabbing the greater than function. I'll also need to reposition my Boolean indicator and slider to place them inside of my loop. I'll wire both the temperature reading and the slider value into my comparison function. The output of this will either be a true or false that I'll wire into my Boolean. Our last step is to customize the scale of the slider to bring it more in line with our temperature measurement. I'll do this by double-clicking on the scale and setting it between 70 and 90 degrees Fahrenheit. Our limit will be approximately 84 to 85 degrees. When I run the VI, we should see that the Boolean lights up once that temperature is exceeded. I'll press the run arrow now, and then press the thermocouple. You'll see that very quickly the Boolean lights up. If I let go of the thermocouple, the trend once again goes down, and once it goes below 85 degrees, the Boolean goes off. Now, if you've had trouble following the execution of this program, there's one last tool I want to tell you about. Highlight Execution, which is something that you can access from the menu bar, allows you to watch the execution of your program as it runs. You can actually see the data flowing down the wires, so we can watch data being produced by the DAC assistant, processed by the statistics VI, compared to the slider, and then plotted on the user interface. In this demonstration, we showed how you can use LabVIEW to create a program that acquires, analyzes, and presents data. However, we've only scratched the surface of what LabVIEW can do. Take the next step and learn how you can use LabVIEW in your applications. Thanks for watching.